Alright, so now let's have a look at example 20. But before I do that, let's look at the sentence above. So see if you agree with this statement. So if I have an integer n, so n is an element of your integer z's, then 2n will always be even. Again, as I said before, if you're doubling a number, 2 is always a factor. And if 2 is a factor, then it's an even number. And 2n plus 1 is odd. Do you agree? Because if 2n is even, because a number is either odd or even, right? So if it's not even and 1 after it, then it must be an odd number. So if 2n is even, because 2 is a factor, then 2n plus 1, which is a number after that even number, it must be odd, because numbers are either even or odd. So we're going to use that idea that 2n is even and 2n plus 1 is odd to prove example 20. So example 20 says, prove that n squared is odd if and only if n is odd. So we've got two ways here. So want to prove n squared is odd. Remember, if and only if is a double arrow, n is odd. So a double arrow means we need to show that if n squared is odd, then n is odd. And we also need to show that if n is odd, then going the other way, n squared is odd. Okay, so there's two things we need to prove, two statements we need to prove. I'm going to look at the backward statement first. So we want to show that if n is odd, then n squared is odd first, because that's just easier. So for starters, let's consider if n is odd, because that's the going backwards. Then we want to show that n squared is odd. Well, how do we do that? Okay, so we want to show the backward statement. Well, suppose, because our statement starting off with is if n is odd. So suppose n is odd. So suppose n is odd. So I'm going to go proof. Suppose n is odd, okay. Well, we can say that n is some two lots of number plus 1, because that's a definition of odd, right? So suppose n is odd. Then we can say that n is equal to 2a plus 1, where a is some integer, because that's a definition of odd. It's double some integer plus 1, because if it's not even, then it's odd. Well, we want to show something that involves n squared. Well, if n is equal to that, what is n squared equal to? Well, n squared is equal to 2a plus 1 all squared. Well, if you see a squared, let's expand it. So we get 4a squared plus 4a, because it's twice and first times second, plus b squared, so that's 1. We want to show that n squared is odd. So if we can rewrite this n squared expression as two lots of something plus 1, because that's a definition of odd. It's twice a number plus 1. If we can rearrange this algebraic expression right now to two lots of something plus 1, then we have shown that it's odd. Well, we can, because we can factorize out a 2 so that we get 2 outside of 2a squared plus 2a plus 1, right? So that I could replace it with an integer b, where b is equal to 2a squared plus 2a, right? And that itself is an element of an integer. Because if you square an integer, you'll still get an integer. If you double an integer, you'll still get an integer. If you add integers, you'll still get an integers. You won't get decimals, right? So this b, where b is 2a squared plus 2a, is part of an integer, which means that by definition, it's two lots of some integer plus 1. So therefore, n squared is odd, because that's a definition of odd. So therefore, n squared is odd. So therefore, we have shown that if n is odd, then n squared is odd. So that was our goal part 1, the backward statement. We wanted to show that if n is odd, then n squared is odd. Okay? Now, we need to show the other way, which is a little bit more trickier, but it's not impossible. We want to show that if n squared is odd, then n becomes odd. So let's show the forward statement that we want to prove that if n squared is odd, then n is odd. So that's our goal for part 2, because we need to show if and only if. All right, so let's prove it. So proof, right. So we are assuming n squared is odd because it says if n squared is odd. So suppose that n squared is odd. What does it mean if something is odd? Well, if something is odd, then we can write that number as 2 lots of some integer plus 1, where t is an element of an integer. Okay, now this is a trick where you go, what? So how did you even come up with that? So again, it's exposure. If you see these little tricks, you just make a list of them so you know when to use it in future. All right, I'm gonna throw this out there. Consider n squared minus 1. You're thinking like, why would I even want to consider n squared minus 1? Look, trust me, it'll make sense in a moment. Okay, consider n squared minus 1, all right? N squared minus 1 is a difference of perfect squares. So we can actually factorize this as n minus 1, n plus 1, right? So that's saying that, well, if n squared is 2t plus 1, well, so that tells us that 2t plus 1, because that's n squared, minus 1 is n minus 1 times n plus 1. So plus 1 minus 1 on the left gives us 2t is equal to n minus 1 n plus 1. So in other words, the product n minus 1 n plus 1 is even. Why? Because we said that t was an integer, and twice an integer is always an even number because 2 is a factor. So we can say that the product of n minus 1 and n plus 1 is an even number. How does this help us? Well, if the product of 2 numbers is even, then one of them has to be even, right? Think about it. If you're multiplying 2 odd numbers, you won't be able to get an even number. And in fact, we'll actually prove that statement to be true in later lessons, because we haven't actually done proof by contradiction yet. But for now, trust me, it is true that if the product of 2 numbers, the product of 2 numbers is even, then one of the numbers is even. I mean, if you think of, you can't prove it through examples, but if you just imagine a few examples right now, like trying to multiply some of the odds together, there's no way you can get an even number because you need 2 as a factor, right? I mean, as I said before, we will actually prove the statement later on, or you will in your homework using proof by contradiction. But for now, take it from me that if you're multiplying 2 numbers and the answer is even, then one of them, at least one of them, has to be an even number. So that tells us that either n plus 1 is even, which means that, so n is odd, right? So if n plus 1 is even, then 1 before it must be odd because the number is either even or odd. Or we have that n minus 1 is even, so n is odd. Alright, so if the number before is even, then obviously the one after is odd, because again, a number can either be only odd or even. So that we've shown that, therefore, if n squared is odd, then n is odd. So therefore, if n squared is odd, then n is odd. So finally, combining both statements, we have shown that n squared is odd if and only if n is odd. Okay, so with mathematical proofs, communication is super duper important, because essentially every line, every statement you write is worth half a mark, okay? So you really need to follow the pattern and the process of writing out and setting out these proofs. So in summary, what have we done just in the last 5 or even more minutes? We established that a number or an integer is even if we double it. So if it's in the form of 2n, because 2 is a factor, then it's even. We also established that a number before or after an even number is always odd, because a number can only be even or odd, right? In particular, if we want to show an if and only if statement, we need to do both arrows. We started off with if n is odd, then we wanted to show n squared is odd. So the if statement tells us that that is what we suppose is true. So we start off with suppose n is odd. Well, what does the word odd mean? Well, an odd means that we can write n as twice some integer plus 1, because that's the definition of odd. Because our final statement we want to prove involves n squared, let's square n. So that gives us 2a plus 1 all squared. Expanding brackets, we get 4a squared plus 4a plus 1. We wanted to show that n squared is odd. So by definition, if we could rearrange this algebraic expression into 2 lots of some integer plus 1, then we have shown that n squared is odd. So if we take a factor out of 2 out, then what we're left over is 2a squared plus 2a plus 1. So we're saying that this is the same as 2b plus 1, where b is defined as 2a squared plus 2a, and that is some integer. B is an integer. Why? Because if you square, multiply, or add integers, you will still get whole numbers. You won't be able to get decimal values. So because of the definition of odd, this is a 2 lots of some integer plus 1. Therefore, n squared is odd. And we finish off that side of the proof by saying, therefore, we have shown that if n is odd, then n squared is odd. Because it's an if and only if, we need to show the other arrow as well, which is if n squared is odd, then n is odd. So to prove it, suppose your if part is true, because that's your proposition. So suppose n squared is odd. What does that mean? What does odd mean? Or odd means you can write that number as 2 lots of some integer. So that's why I've got t in an element of z, so a comma, letting the reader know that this t, which I've just randomly defined, is some integer, right? So by definition of odd, n squared is 2 lots of some integer plus 1. Now, this is just a trick which you have to learn. Well, if I want to show that n is odd, we'll consider n squared minus 1, because we can factorize n squared minus 1 as a difference of perfect squares. We said n squared was an odd number, so let's replace it in. So 2 lots of some integer plus 1 minus 1 gives us 2t. On the right-hand side, it's the product of our linear factors, n plus 1, n minus 1, because it's a difference of 2 squares, or perfect squares. So on the left-hand side, because it's 2 lots of some integer, that is the definition of an even number. So that tells us that n minus 1 times n plus 1 is an even number, because t was some integer, and it's twice some integer, which is by definition an even number. Now, take it from trust, and you will eventually prove this for homework anyway, that if you multiply 2 numbers, which is even, then one of the numbers has to be an even number. So if the product of 2 numbers is even, then one of them has to be even. So that tells us that because n minus 1 times n plus 1 is even, so either n plus 1 is even or n minus 1 is even. If n plus 1 was even, then that means the number before that must be odd, because the numbers are either even or odd. Or we have the other case that n minus 1 is even, which means n is odd because the one after is odd. So therefore, we've shown that regardless of the possibilities, we always end up with n being an odd number. So therefore, we've shown that if n squared is odd, because that's our starting supposition, we assumed that, then our final result is n is always odd. And because we've shown the 2 arrows, the if both ways, therefore we have shown the if n squared is odd if and only if n is odd. So you might need to read through this again and make sure you fully understand the layout and the communication of proofs, because literally every single line of a proof is worth half a mark. In particular, even these little bits of like comma, A is an element of Z, or where B equals this thing is an integer, or comma T is an integer. Like if you don't write these little bits, because then you won't get full marks, because these tell us the definition of odd and even numbers, because they have to be elements of integers. If it's not an integer, then we can't talk about evens and odds. There's no such thing as even and odds when we're talking about